Thank you for the introduction, and I also want to thank the organizers for inviting me, and also I want to thank Dong for doing all the heavy lifting of introducing all the basic stuff about quantum algorithms. So yeah, hopefully my job will be easier after those tutorial. Yeah, so I will cover two things: the Heisenberg limit and the early fault-tolerant quantum algorithms. So the first part is mainly about Heisenberg limit, and second part is about early fault-tolerant quantum algorithms. And I think the unifying theme is quantum phase estimation. Yeah, so I will introduce all these things as we go along. Yeah, so one of the most important questions in quantum algorithm is that can we solve a practically useful problem on a quantum computer faster than on a classical computer? Right? So this is the whole motivation of this field. And one place to look for such a problem may be quantum chemistry, simply because quantum chemistry is quantum in nature, so it might make sense to use a quantum computer to simulate it. And the basic problem in quantum chemistry is finding the ground state energy. Equivalently is finding the lowest eigenvalue of a Hermitian matrix H, which is your Hamiltonian. And in order to claim that we gain quantum advantage, we need to be able to beat classical algorithms. However, for quantum chemistry in particular, classical algorithms already achieve very high accuracy. For example, density functional theory can usually take you to a precision of 2 to 3 Kelvin per mole, according to this paper. Whereas the chemical accuracy we want to achieve is like 1 Kelvin per mole. So you see, it's actually, classical algorithm already take you pretty close to the precision you want to get. And in order for quantum algorithm to be useful, you need even higher accuracy. So this means that if we want to really design a useful quantum algorithm, we need to really care about how the cost of quantum algorithm scale with the precision. And it is not a trivial problem, actually. So when we talk about quantum computing, the precision scaling is usually more complicated than in a classical scenario. As an example, we may look at the Hamiltonian H. So whenever I say Hamiltonian, it always means a Hermitian matrix. And you can write it as a sum of Pauli terms. So each of these pi is a multi-qubit Pauli with a couple of coefficients before. And now, assuming we have such a Hamiltonian, and also assume we have an exact eigenstate psi, how do we compute the eigenvalue lambda, right? So in the classical setting, this is almost a trivial question, because you can just do one matrix vector multiplication, multiply h to psi, get a vector, and compute the inner product between two vectors. So you use these two basic operations, and you can compute everything to machine precision without any problem. However, on a quantum computer, you cannot really do that. You can use something like block encoding H, and then do this block encoding applied to a quantum state, and then try to compute this overlap, right? The kind of thing Dong introduced just then. But that will require actually a lot of resources. So maybe a more direct way to do this is to just measure each Pauli operator, measure each pi. So in measuring, you will get a lot of 0-1 outputs, and then you take average to get the expectation value for each term, and then add up all the Pauli terms in order to get the expectation value of this whole H. So this is a natural way to do things in a quantum setting. And to measure a single Pauli operator, for example, to measure this x tensor x, what you need to do is to basically write it down this way. So you have x tensor x is what you want to get. Now you decompose it into Hadamard tensor Hadamard times z tensor z times Hadamard tensor Hadamard. So you can do this because x is equal to Hadamard z Hadamard. So if you don't remember what they are, Hadamard is 1 over square root 2, 1, 1, 1 minus 1. X is 1, 1. Z is 1 minus 1. So basically what we do is to apply 2 Hadamard gates to 2 qubits on this state psi, and then measure in the computational basis to get the expectation value for z. And that will give you the expectation value for x tensor x. So even for a single term, it seems like you already need to go through a lot of operations. And so when we do measurement, we will get output, which is 0 or 1. And what we can ensure is that when we compute this -1 to the m hat, the expectation value will be exactly what we want, this expectation value with respect to the quantum state. And then we take average over ns samples. The variance decays like 1 over ns, which is the same scaling you get in Monte Carlo algorithms. So this is for one term, right? We need to do this for all terms. And we can measure some of them simultaneously. So if two terms commute, you can measure them simultaneously. And so basically, the total cost of estimating, just reaching absolute precision for estimating the expectation value of h, scale like sum of norm of h squared divided by epsilon squared. So what norm exactly, it depends on your measurement scheme. Like different scheme will give you different norm. But roughly, it's like this: some kind of norm squared divided by epsilon squared. In the classical scenario, when you compute this state psi as stored as a vector in your classical memory, and you'll be able to use it however many times you want, right? But here, each time you do measurement on a quantum computer, you need a new copy of psi. So roughly, you need this many copies of psi. And because measurement destroys quantum state. So what this means is that even just reading out the eigenvalue from an eigenvector requires some non-trivial process already. And there is a lot of room of optimization. In particular, like right now, I'm talking about very naive way of doing it, but more sophisticated ways, like quantum phase estimation, can achieve the same with a scaling that is epsilon inverse in terms of the evolution time. So compared to epsilon to the -2, it's a quadratic speedup. And this is called a Heisenberg limit and uses a single copy of psi. So this difference actually, so right now, when you look at it, it's probably just epsilon to the -2 to epsilon to the -1. But in terms of runtime in practice, this is a huge difference. Like say you want epsilon to be 10 to the -3, right? According to this 333 criteria proposed by Ling, then you will need this. You will need 10 to the 6 copies of this quantum state. This you will need evolve for 10 to the 3 evolution time. So this one will be much more manageable. Like even on like near-term devices, because like if you maybe not on near-term devices, but still, like sometimes if you want to reach very high precision, such as chemical accuracy, this kind of scaling will give you an astronomical number, where this one will give you something more manageable. So we may consider different algorithms at different development stages of quantum computing. So right now, we're in the NISQ era. So the quantum devices are really, really noisy. So we want an algorithm to be kind of robust to the noise. And this is the reason why we consider things like variational quantum eigensolver or QAOA, which we will hear more about on Thursday. But all these algorithms give you epsilon to the -2 scaling because you need to compute expectation value at each iteration. And they run into all kinds of problems with classical optimization. So they may not eventually be what we want to do when we finally have a fully fault-tolerant quantum computer. For a fully fault-tolerant computer, we want to do something along the line of quantum phase estimation, which gives you this epsilon inverse scaling rather than epsilon to the -2. So when we have a fully fault-tolerant quantum computer, then our main consideration will be the total runtime, which is dominated by the number of non-Clifford gates. And at that point, we may also consider issues like parallelization, energy consumption, and anything else you might consider right now for a supercomputer. And we may also have some stage in between. So when we first have a fault-tolerant quantum computer, we may still have a non-negligible error rate, logical error rate. So that means, like, on top of optimizing for the total runtime, we also need to care about measures like circuit depth and number of qubits, which actually affect your error correction overhead. So So there are two kinds of precision scaling. Yes, please.
Back to that slide, why is it dominated by non-Clifford gates?
This is simply because when you have error correction, the amount of resources needed for non-Clifford gate is much, much larger than for a Clifford gate.
And also, we're going to have a tutorial on this today.
Yeah, like in the afternoon. So. Yeah, so we have two kinds of precision scaling. One is the Heisenberg limit, another is this epsilon to the minus 2. You have the same example for both. Here I will go a little bit more into it. So we consider the quantum version of parameter estimation. So we all know, like in classical setting, we have parameter estimation. So given a probability distribution, and we might want to estimate some parameter out of it. So this is a quantum version. So we want to estimate the parameter data from a parameterized quantum state raw theta. And raw theta is somewhat sensitive to theta. So their sensitivity is upper bounded by something. And then, so the classical counterpart is you replace this quantum state by p theta, which is a probability distribution. So the question is like, how many examples from how many copies of the quantum state do you need in order to estimate theta to precision epsilon? So there is an information theoretic lower bound saying that you need epsilon to the minus too many examples in order to extract this parameter theta. And the same is also true for the classical setting. However, there are things you can estimate in the quantum world beyond this scaling. For example, if we want to estimate an eigenvalue to precision epsilon, we can use quantum phase estimation with the exact eigenstate that requires runtime epsilon inverse, which I mentioned previously. So, and this is called a Heisenberg limit because it is, again, an information theoretic lower bound. So you can prove that it requires at least this much evolution time in order for estimating the precision to epsilon. So one can say this is actually the fundamental limit set by quantum mechanics. You can never go beyond that. And this is the limit we want to achieve in our algorithms when we want a classical readout.
How do you prove this thing?
Yeah, so you can just say, so you have a model for your quantum algorithm, right? So you start from some state, evolve with this Hamiltonian. Well, I haven't written down Hamiltonian, but then your state will deviate from each other if you perturb the Hamiltonian by a little bit, right? Say by something like by perturbation of order epsilon, that will perturb your eigenvalue as well. And you need the evolved state to be like a constant distance from each other in order to be able to distinguish them. And the amount of time needed for that to happen is like epsilon inverse. So is that clear? Yes.
So what's the fundamental reason that leads to the existence of the Heisenberg limit?
Well, I think that comes from the unitarity of quantum evolution. Like if you have some small deviation during your time evolution, that can only accumulate linearly in time, right? And if you have an epsilon perturbation, in order for that to reach a constant amount, you will need epsilon inverse amount of time. So I think that's unitarity and the linearity are the main reasons. I think there was a.
I was going to ask sort of the same question.
Oh, I see. Okay. Yeah.
So if there's a quantum algorithm that can achieve the Heisenberg limit, can we also develop a quantum algorithm that with scaling like the epsilon minus alpha, with alpha is between 1 and 2?
Sorry, is it smaller than 1 or larger than 1?
Sorry.
You mean alpha goes between 1 and 2?
1 and 2.
Yeah. That's a really good question. So sometimes you can do that, and there are some benefits. Like you have a trade-off between the total runtime and the circuit depth. Actually, there are works on that along the line of phase estimation. Yes.
Can you clarify one more time the difference between the assumptions for the two information theoretic lower bounds? Presumably they're not both lower bounds.
Right, yeah. So I would say this lower bound is for a quantum state. You have a fixed state, and this is you will need this many copies to get the accuracy. But here it's a dynamical process, so that's different. Like, yeah.
So is there a reference where I can find the proof, like the precise statement of the theorem and the proof of this
Heisenberg limit?
Yeah.
Well, yeah, people have written down some kind of proof using the quantum Fisher information, but I wouldn't say that's rigorous proof. So actually, I have a recent paper on Hamiltonian learning that contains a rigorous proof, so I can tell you about it like offline. Yeah. Any other questions? Yes.
Why is the name Heisenberg attached to it? Is there some kind of commutator relationship there that the whole
Yeah, actually,
likely?
yeah, that's a good question. So I'm not really sure about the historical origin, but I think it has something to do with the time-energy uncertainty principle. So, right, but you need some concrete version of time-energy uncertainty principle to formulate this limit. Yes, please.
So you said you want to focus on useful stuff. So in this case, you're saying we know the exact eigenstate.
Right.
So would there be a situation in which we know the exact eigenstate and yet like we somehow, because doing it classically, you said it's just a matrix vector multiplication. So do we not know the Hamiltonian, or is it just such a giant matrix vector multiplication that we can't do it?
Right. So when I talk about practical things, I will not assume that you have a exact eigenstate. Here, I'm just talking about lower bound, right? Like
Okay.
even if you have an exact eigenstate, you still need this much total evolution time.
Yeah.
Yes, please.
I have one more question, so more probably for the word Heisenberg limit, right? So the Heisenberg uncertainty principle for unbounded operators, where your argument that if you perturb by time t, it's 1 over t just doesn't work because, the operator is unbounded. So isn't there a little bit of a clash? I mean, are you not doing some approximation here, approximation there, and then you cut some corners?
Right. So I don't think so. You cannot derive the Heisenberg limit simply from the time-energy uncertainty principle. This is something else. So I'm assuming everything is bounded. Like you only work with bounded operator, and you can prove this kind of thing. If you have unbounded operator, indeed, I think you can surpass Heisenberg. So you'll get a different Heisenberg limit. So here I'm talking about Heisenberg limit in terms of the evolution time. So but it is also formulated in terms of the number of entangled copies and also the energy in your system. So there are many ways to formulate it, but always you will have some kind of measure that limits the precision you can possibly achieve. And it always scales like this. Yeah. So here it's maybe a bit simplified, but they are more. Yes, please.
Is this kind of quadratic improvement in the number of samples of a different kind than what we get in like a Grover type speedup?
Right. Yeah. So this is closely related to Grover speedup, but you cannot just apply Grover algorithm to get this kind of speedup. It's totally different. Any other questions? Okay. Yeah, I really appreciate the questions. Please keep asking. So before I go into any detail, let me actually next I will present the simplest example I know of an algorithm that achieves the Heisenberg limit. But before I do that, let me introduce some notations. So we have a target Hamiltonian H, which is a Hermitian matrix of size 2 to the n times 2 to the n, where n is the number of qubits. This you have already seen in Tong's talk. And its eigenvalues and corresponding eigenstates are lambda k and psi k respectively. So lambda k is eigenvalue, psi k is corresponding eigenstate. And I arrange the eigenvalues in ascending order and assume like the ground state is not degenerate. When it is degenerate, actually it also works fine, but for simplicity, I assume it's not degenerate. So lambda 0 is the smallest eigenvalue. It's also the ground state energy. And psi 0, we call it the ground state. For other states, we call it them like excited states. We assume access to a quantum state phi for initial guess for the ground state. So of course, it would be really good if phi is exactly the ground state, but it doesn't have to be. So as long as there's some overlap, it's fine. Like I will make a rigorous statement later. So we need some way to access this Hamiltonian H, right? Because it's an exponentially large matrix. But we could use block encoding, but for near-term scenario, it's easier to use time evolution operator, which you can obtain through Chorter and like Chorter decomposition, which Dee will give a talk on later today. And so we can apply control the time evolution with this Hamiltonian H, and that will give us information about this Hamiltonian H. Here, tau is a rescaling factor, so we need to make sure the spectrum of this rescaled Hamiltonian lies within some interval in order for our algorithm to work. And we also use those asymptotic notations. We use the standard big O notation. And we will sometimes write O tilde to hide this polylog vector. So if we keep track of all the polylog vectors, it's going to be annoying. So sometimes I just hide it. And I'll use this omega to mean like fx is at least as much as like this g of x. And I will also use this omega tilde to hide the polylog vector in this big omega. So I've already seen these notations, and I'm just make sure that you understand what they mean. So yeah, so basically the simplest algorithm for estimating the ground state energy is this based on this Hartman test circuit. So Lin had already introduced it yesterday. So in this circuit, we start with two registers. The first register is the ancilla register that contains only a single qubit, and the second register contains this initial state phi. And what you do is you first apply Hartman gate to the initial state, and then apply controlled time evolution. So the time evolution is controlled on the first qubit. You only evolve when this qubit is in state 1. When it's in state 0, you do nothing on the second register. And then you apply a Hartman gate or a Hartman gate, a inverse phase gate followed by a Hartman gate, depending on the scenario. And after this gate, you do measurement. So what you get out of this circuit is that you can compute expectation values of this form. So it's the expectation value of the time evolution operator with respect to the quantum state phi. And you need to compute the real and imaginary parts separately. So when this gate is chosen to be the Hartman gate, you will get the real part. And when it's chosen to be this whole thing, then you will get the imaginary part. So I will actually derive this in this slide. So what you do in the Hartman test circuit is that you start with this state 0 tensor phi. Right? This is the initial state, that is product state. You apply Hartman gate, so 0 goes to plus. And then you apply control time evolution. So when you apply control time evolution, your quantum state is actually divided into two branches. Right? So when you have 0 tensor phi, the control time evolution doesn't do anything, so it just remains what it is. When you have 1 phi, then you apply a time evolution operator. So in the next step, you apply Hartman gate. So 0 is mapped to plus, 1 is mapped to minus, right? And then we write down the plus and minus states in terms of the computational basis states. So plus is 0 plus 1 divided by 1 over square root of 2. So you have 1 over 2 here. And similarly for minus state. Now we recombine everything. So we move 0 tensor phi and 0 tensor e to the minus ith phi together. And everything involving 1, we move them together to get this form. So why do we do that? This is because now we can have so these things actually have physical meanings. So when we measure the first qubit, which is this qubit, we will get 0 with probability like this whole thing norm squared divided by 4. So because there's a 1/2 here. We will get 1 with probability of the norm of this whole thing squared divided by 4. So when we compute the expectation value, so that the output we denote by m hat, which is a random variable, it takes value 0 and 1. When we compute the expectation value of -1 to the m hat, then it becomes like this. So this is the probability of getting 0. This is the probability of getting 1. You compute the difference, and then it will give you you can actually compute this expression just by expanding everything, and then you'll see actually the expectation value is exactly the real part of this thing that we want to compute. And similarly, you can do the same to get the imaginary part. So this is basically what this circuit does. It helps you compute the expectation value of a unitary. Yeah, any questions at this point? Okay. Yeah. So we can do the same thing to get the imaginary part, just replacing the second single qubit gate we applied by something else. So for any t, so t is a parameter we can choose, right? So we can estimate this expectation value by a noisy signal. So we have a S of t, which is a signal. That is the expectation value we want to get plus some statistical noise. So at this point, everything becomes classical. You have a classical signal that is complex value with some noise. This signal, in principle, gives you everything you want to get about a Hamiltonian, because we can write down the eigendecomposition of H, and we do that to write down eigendecomposition for this time evolution operator, and then you plug it into this expression. You will be able to write down this expectation value in this way. So you can see it's a sum over k, and for each k, you have some frequency lambda k. So this signal is rotating with a frequency lambda k. And lambda k is actually the eigenvalue of your Hamiltonian. So, and here there's some weight attached to each eigenvalue. So basically, if you want to get say the ground state energy of H, you only need to get, say, all the frequencies, right? And one of them will correspond to the ground state energy. So at this point, it boils down to a classical signal processing problem. However, it's also kind of different from the usual classical signal processing problem you always see, because there are 2 to the n many different frequencies. And many of them are extremely close to each other. So basically, you have some kind of a continuous spectrum, like for a lot of places. And you don't care about all the frequencies equally. Rather, you only care about one of them, which is the ground state. Right? So this compels us to develop something different from the usual classical signal processing techniques. So we can, as soon as we have this signal, we can obtain eigenvalues of H by processing the signal and getting the target frequency. And I will explain how to do that in a very simple scenario in the next few slides.
So in principle, you only get this for a specific value of time, right? You don't get this as a function of time, unless you run it many times.
Yeah, you do run it for many times. You do run for different H. And actually you get to choose T, right? So that's also a difference from the classical scenario where you usually just have some T that is given to you. But here we have the freedom to choose what kind of T we want. Yes, please.
So those amplitudes are like your Fourier coefficients. So
exactly.
You have to estimate that for multiple values of t. Like for every single time, you have to repeat this many times to get the Fourier coefficient.
So one way to do that is indeed you can try to get a Fourier coefficient, but I will actually show that it's not the optimal way. But I think that's a good idea. Like people indeed do that, like sometimes. Other questions? Right. So so the simplest scenario is single frequency, right? We have a lot of different frequencies, but if we right now I just want to propose the simplest algorithm to get the Heisenberg scaling. So that's why I use an extremely strong assumption that phi is exactly the ground state. I will not keep using this assumption. This is only for this example. So if we have phi being exactly equal to ground state, then the signal we get will be e to the minus I lambda 0 t plus some noise. So there's only a single frequency. It's just some rotation on the unit circle, right? And in a complex plane plus some statistical noise. So now the goal is to estimate lambda 0. So the signal can be generated from the Harman test circuit. And we want to estimate lambda 0. So we need some assumption because if, say, lambda 0 can be an arbitrarily large number, then you'll need to sample t in a very fine way in order to resolve the like a 2 pi phase difference. So we assume lambda 0 is in -1 and 1. And this can always be done by rescaling the Hamiltonian appropriately. And we want to estimate lambda 0 to precision epsilon. So one way we can do that is to fix t, say pi over 2, and then just estimate this thing by averaging out the noise et. And then we take a log. That will give us theta. Sorry, not theta, this lambda 0. And this thing has the, because you need to average out noise, right? So that needs epsilon to the minus 2 many samples in order to reach epsilon frequency, the same scaling you see in Monte Carlo method. So I will outline a method that uses log epsilon inverse many examples, epsilon inverse total evolution time, ignoring log factors. So by total evolution time, I mean that I will generate example ST1, ST2, all the way to STNS, and the total evolution time is everything added together.
But in doing this, I mean, once you've obtained S of T1, right, you've made this measurement, you've destroyed the system, right?
Right,
So you
yeah.
cannot just continue on to T2. So
Right, you do it again. You prepare the state again and then run for T2 in a separate experiment. Yeah, there's, yes.
Is there any cost with rescaling the Hamiltonian, like any cost in terms of, for example, like time or?
Sorry, could you speak louder?
Yes, so is there any cost with rescaling the Hamiltonian properly that you mentioned this lambda to be between -1 to 1?
Oh, yeah. So in this example, it's sufficient to just scale lambda 0 appropriately so that it falls in this interval. But yeah, in a practical scenario, like you have many eigenvalues, right? You might want to make sure that lambda 0 is the smallest one. So that means you need to, and because you're mapping everything into a circle, right? So you kind of lose this ordering. So you need to be able to keep track of ordering. That's why when you don't have a perfect eigenstate, you need to rescale the entire Hamiltonian so that the spectrum is containing some kind of interval like this. Yes.
So by rescaling the Hamiltonian properly, do you mean you have accurate estimation for the ground state energy?
No. You have a rough upper bound of the spectral norm, the operator norm of your Hamiltonian, and that will be sufficient for.
But in that case, like suppose the ground state energy is of O1, and you use maybe big On to rescale the energy, then the rescale ground state energy could be really small.
Yeah. So that's why the rescaling factor will come into the cost. So you need to get higher precision, right? So in your example, it means you need precision epsilon over n in order to get the ground state energy. But that's a very big practical concern. But in theory, it's only like a poly in system size, right? Yes.
How do we know what the rescaling factor is?
So as long as you have an upper bound for the norm of the Hamiltonian, you can always rescale it, like to make sure all the eigenvalues are contained in -1 and 1. You just divide your Hamiltonian by the norm, right? Yes.
So, I think just following up on this question, I guess you consider the Heisenberg limit to include also the rescaled epsilon. This sort of, yeah, okay.
Yeah. So, but like, so there is a linear relation between the rescaled one and the unrescaled one, right? Which is independent of this epsilon. So when you achieve Heisenberg limit for one, you achieve Heisenberg limit for another because it's like asymptotic scaling. Yes.
how do you average out the noise?
So let's say the noise is unbiased, like it has mean 0, then you can average noise. But you cannot always do that if the noise is biased, then you cannot do that. But in this method I'm going to talk about, actually we can tolerate biased noise.
Yeah. Also for the rescaling question, so after rescale, so what's the time scale for this T1 to Tn?
Oh, sorry, what do you mean by time scale? Like in terms of what?
Because maybe after rescaling the Hamiltonian, and this T is also need to be of certain scale.
Right, yeah, so T, the largest T is of scale 1 over epsilon, which you will see later. Like if you take into account scaling, say you scale with n, then the largest is going to be n over epsilon.
I guess the point is in your big O of epsilon inverse, the big O is with a fixed norm of the Hamiltonian.
Right, yeah. So here I'm assuming lambda 0 is in this, right? So I haven't taken into account the normalization factor in this calculation. Any other question? Yes.
If it was on matters,
Sorry, could you be?
does the value of t matters?
Sorry,
So let t equals to pi over 2. So does the choice of t matters to the result?
That's what?
That the chosen of t value matters to the result.
Yeah, it definitely matters, but here this is just an example. I'm not going to really do that. Like it's a kind of not so optimal way of doing it. Yes.
When you say like t equal pi over 2, do you mean that t1 and t2, all of those are just pi over 2?
T1.
Like at the bottom you have t1, t2, etc. Are all of those
Oh,
just
no,
pi
no.
over 2?
Sorry. I think this slide may be confusing. So that's a separate method. So here I'm telling you, if you don't think about it too hard, this is one way you can come up with. But if you think about it really, really hard, you can come up with a better method. So these T1, T2 have nothing to do with it.
We don't know how to choose them yet, or are we?
You will see how to choose them. Okay. Yes.
I'm a bit lost. Could you remind me what theta is?
Sorry. Theta is minus lambda 0.
Wait.
Theta is, or you can view it as lambda 0. Like,
Okay.
yeah.
Sure.
Sorry. This is a typo.
Okay.
No questions?
Yeah,
Oh.
I have one more. Is it fair to say that you are somehow looking at the polynomial in T, right, more like instead of the individual value? I mean, does that give you an advantage? If you think of this as a polynomial in T, where you can, I mean, that last line indicates that if you choose these different times, even small of them, you gain a lot of extra knowledge.
You mean like viewing S as a polynomial?
Like you view S of T as a polynomial in T and then discretize later. But then a polynomial, of course, contains way more information than a single value.
Yeah. So you mean do some kind of fitting for the signal? Yeah, I think it's kind of like that. Yeah, I think maybe you can view it as a specific way of doing fitting. Yeah.
And it's better than that you know that it should be exponential of some kind, right? So you don't need.
Yeah. So maybe let's move on to the method. So the basic building block of the method is the following. So suppose we already know minus lambda 0 is in some interval between A and B. Like we already know like it's between the interval between like -1 and 1, right? So initially you just set A and B to be -1 and 1. So suppose we know such a pair of A and B. Then we want to determine the following. So minus lambda 0 is somewhere here. We want to determine whether it's here or here. So the interval is divided at this point of like 2/3 and 2/3. So you see these two parts actually overlap in the middle, right? So when minus lambda 0 is in the middle, both scenarios are acceptable. When lambda 0 is in the leftmost third, then we want to be able to determine that this is indeed true. And when minus lambda 0 is in the rightmost third, we want to determine that this is indeed true. So this is the basic building block of our algorithm. We want to be able to do this. So if we can do this, then we can basically do a kind of binary search. So basically, we start with some interval of between A and B, and then after doing this, we will reduce the uncertainty by 1/3. So A and B will. So if we just keep doing this for log epsilon inverse many steps, then A and B will converge to this minus lambda 0 from both sides exponentially. So that's why in order to reach epsilon precision, you only need log epsilon inverse many steps of doing this thing. So next, the question is how do we do this? How do we go from A to B like to a smaller interval? So the way we do that is to design a function of this minus lambda 0, which is the following. It's just a rescale and the shifted sign function. And the important thing about this function is that it can be computed by this signal for a specifically chosen T star. And T star is chosen to be pi over B minus A. And this whole thing is multiplied to a phase vector. And so the function looks like this. So this is A and B. Your minus lambda 0 is somewhere in here. So if your function value is upper bounded by 1/2, which means it's below this point, then your minus lambda 0 must be in these two parts. If your function value is greater than -1/2, it must be in these two parts, right? So just by computing the function value, you will be able to solve this iteration, which is you find a smaller interval that contains this minus lambda 0. And why is it important to have an overlap, right? This is because we want to be able to tolerate error in this function. So we only need to evaluate this function to precision 1/2 in order to locate this minus lambda 0. So that's constant precision instead of something that scales with epsilon. And we want to get a high confidence level, so you can do this by majority voting. So basically, you just repeat the procedure log delta prime inverse many times, and then do a majority voting, which is you take the outcome that is the majority, and then and take that to be the outcome you believe, and then that will get you a confidence level that is like arbitrarily close to 1. So this is procedure for solving this problem of going from A to B to a smaller interval. So any question? Yes.
So what do you mean by confidence level here?
Confidence level, like there is some error in ST, right? And that error is stochastic. It's like there is some probability that it's always wrong, like in a specific direction, right? So there is some probability of the procedure failing, but you can ensure the probability is arbitrarily small. Okay. Yes.
I'm sorry, can you reiterate why constant precision is enough?
Yeah. So say I can only evaluate this thing to precision 1/2. Say this function value is here, right? And then it may be wrong, so it goes to somewhere like here. But you will still be able to locate this minus lambda 0 within the correct interval.
So what is the special thing about this 1/3 interval? Like, why can't you make like 1/4 or something?
You cannot do it 1/4. Sorry, what do you mean? Like it has to be greater than 1/2, right? So in order to have this overlap, it has to be greater than 1/2.
Yes.
So that's
anything greater than half will be okay.
The 1/2 will not be okay because
anything greater than half, so half plus epsilon.
Right. Yeah, that would be okay. Yeah, 1/2 plus epsilon is probably not ideal. Like it's constant beyond 1/2. Like, yeah. Right. So the important point here is that this T star will scale with B minus A. So as B and A get close to each other, you will need to increase this T star. And that will increase the cost for generating this S of T because you will need evolve for a long time. So at the last search step, the distance between B and A will be on the order epsilon. And you will need to choose T star to be basically epsilon inverse. And the cost of the last step, you can compute it in this way, is basically T star times the cost for majority voting, which is roughly epsilon inverse. You can ignore the log factor. And the total cost is the cost of, like you just add a cost from each individual step together. So the cost for the last step is like this, and the cost of the previous step is 2/3 of that, and then the cost of the 2 steps from the last one, you have 2/3 squared, right? And you have a geometric series which you add up together to be a constant. So this is the total cost. And the delta prime is chosen to be delta, which is, so you want the overall confidence level to be 1 minus delta, so delta prime needs to be scaled down a little bit by the number of steps. So that's how I choose this confidence level for each step, and then you get a total evolution time for the whole thing, which is epsilon inverse. And the number of examples, which is linear in the number of steps, is log epsilon inverse. We can. So from the previous slide, we have seen we can tolerate a noise level that is 1/2 in the signal. So, and it doesn't even need to be unbiased. Like you can have a biased signal or something like that.
And cost here refers to the number of majority votes, right? I mean, the number of copies you have to do to get the majority vote, right? Is that correct?
Yeah. So that's basically how many experiments you need to run in each time step. And each experiment also have a different cost, which is measured by how long you need to evolve. Right, yeah. And you need to evolve for 1 over epsilon time, so that's why you have 1 over epsilon. Yes?
Can you briefly explain how we choose T again?
Right, so T is here. So in each iteration, you have a pair of A and B. Right, so you just choose T to be pi over B minus A, right? And as B and A get closer to each other, you need to increase this T as well. Any other question? Okay.
Sorry. I just was wondering why is it you only need logarithmically many samples to get the confidence, whereas like other sampling problems, it seems like you need this like quadratically many samples. Is it just sort of a different?
Right. So here, this is because your output is binary. Your output is 0 or 1, right? Your output is either in this interval or in this interval. That's why you can do a voting to boost the confidence level exponentially. Yes.
So using this Heisenberg test circuit, we can generate S. So in this expression for F on the very right-hand side, I can see how we can get some. I can imagine how we can get maybe some sort of a gate that will implement that. But how do we get the imaginary part of that?
So your ST star is a classical. It's something you have already computed from the quantum circuit. You compute the real and imaginary parts separately. So you just compute two numbers from your Heisenberg test circuit, and they are classical output, right? So you have those two numbers written down on your paper, and then you multiply by this factor, which you also know, and then you take the imaginary part. So then this is done classical.
Wait, so then where's the quantum part?
The quantum part is how do you generate this ST star?
Okay.
Right. So that requires the Heisenberg test circuit. Right. So this is a summary of what we did. This is a single qubit phase estimation. We can use Heisenberg test circuit to estimate the eigenvalue given the corresponding eigenstate with Heisenberg limit scaling. And it is robust to constant amount noise. And more precisely, you have this kind of complex scaling, which I will not restate. So this is for single qubit, and we have the extremely strong assumption that we have the corresponding eigenstate. Right? So what if we don't? What if we only have some rough guess of what it is? So then we will need to use so then we may need to use this multi-qubit version of quantum phase estimation. So in the next tutorial, I will talk about the method that doesn't use this, but here I will first show you how to use this multi-qubit quantum phase estimation to do that. So in multi-qubit quantum phase estimation, we have two registers, the same as before, but the first register contains more than 1 qubits. So this register we call the energy register because it will, upon readout, it will give you the eigenvalue of your Hamiltonian, which is in some sense the energy. So that's why we call it the energy register. And this is the state register. So here we assume the state register is prepared in this state phi, which is the initial guess for the ground state. But it doesn't have to be exactly the ground state. What you do in this phase estimation is you apply a Heisenberg gate to each of those ancilla qubits. And then you do controlled time evolution. And then you do an inverse quantum Fourier transform. And then you measure the energy register. So upon measuring, the energy register will give you a bit string that we call M hat. And you can rescale this bit string in order to get something that should give you the eigenvalue of your Hamiltonian. So you don't have much control of like what eigenvalue it is. So you have 2 to the n many eigenvalues, right? So which one it is, it depends on your state phi. So that's the rough outline of what quantum phase estimation does. And then I will go through how this circuit operates. So any question at this point? Right. Sorry? You need to do it multiple times when phi is not a perfect eigenstate. Yeah. So our initial state is O0 state tensor phi. We apply Heisenberg gates. So all the 0 states become plus state. And the tensor product of plus states actually give you a superposition of all bit strings. So this may not be obvious when you see it for the first time, so let me write it down. So plus state is superposition of 0 and 1, right? And if you have 2 plus states, that's 0 plus 1 tensor. You can just write it out. It becomes 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Right? So it's the superposition of all 2-bit strings. And the same is also true when you go to more copies. So that's why we have a superposition of all bit strings from j to 0 to 2 to the r minus 1, where r is the number of angular qubits. Now we do control the time evolution. So what this means is that you apply this time evolution operator to phi, but how long you evolve depends on j. So that's why it's called control time evolution. So basically, we get a superposition of all the times, like with this tensor product with j. And then we express this initial guess we have. So phi is our initial guess for the ground state. We expand it in the eigenbasis of h to write it in the following way. So this is the state we have in QPE, right? We replace this phi by the eigenstate expansion to write it in the following way. So I move the summation over k to the front because I want to focus on this part. And what inverse quantum Fourier transform does is that it takes j to a Fourier mode. So j is, you may view it as a vector that contains only one entry that is non-zero and takes value 1. And just in the usual discrete Fourier transform, it will be mapped to a discrete Fourier mode, right? So the same thing happens with quantum Fourier transform. So this is what you get. And so we use this relation in this state expression we have here. So j is replaced by this Fourier mode. So you have something like this. So this is the quantum state in quantum phase estimation that you have at the end of the computation before you do measurement. So when you do measurement, you just get a random m, and which m you get depends on the value of this thing and also ck. So it may look very complicated at this moment, so I will try to simplify it in the next few slides. Any question at this point? Yeah, gamma is defined to be this thing. Yeah. Oh, yeah. Sorry about that. Yeah. Yeah. So yeah, we just write this whole thing as gamma theta. So theta is this big thing up to, without this j. Right. So the reason why QPE works is this gamma theta approximates the Dirac delta function. So this is the state we had from the last slide. And gamma theta, you replace it with delta theta, where delta is the Dirac delta function. And this is what you have, just replace gamma with delta. So Dirac delta function is only non-zero when these two are equal, right? So basically, you only have a single m that gives you a non-zero amplitude. So basically, you need to replace this m with something corresponding to lambda k with appropriate scaling, right? So essentially, this is the quantum state you get in the quantum phase estimation before you do measurement. So now we measure the energy register. This is the energy register. So we will be able to get one of these numbers corresponding to sum of the k. So we will get this number, 2 to the r tau lambda k over 2 pi, represented in a binary way. You get 0, 1, 0, 1, something like that. And that will correspond to an eigenvalue of Hamiltonian, although we don't really know which one it is. So there is actually a probability distribution. So the probability of ending up with lambda k is actually the ck norm squared, ck modulus squared. However, this is the idealized version of quantum phase estimation. So I'm basically just replacing this kernel by Dirac delta function, but it isn't exactly the Dirac delta function. And that has actually important implication in terms of the cost of the algorithm, which I will discuss next. So any question at this point?
So why is that quantitative integer?
Why is that integer? It's not necessarily integer, but here I'm, yeah, suppose it's an integer, then this is true. Yeah, so this is very rough intuition. Like when you write down error bound, you should not do this. Yeah, this is not necessarily integer. Right. Okay, so everything depends on this kernel, right? Like we wanted to approximate the Dirac delta function. And we can actually write down a closed form expression for this kernel. So it's just summing up every like root of unity. And so you get a closed form expression that looks like this. And with this kernel function, we'll be able to simplify the quantum state in this way, which we have already seen before. Measuring the energy register M, use M with probability that's like this. So in the idealized case, the probability is simply the CK modulus squared, right? But here, you'll like all the K will have some contribution that depends on this kernel. So we can interpret what happens in the following way. Suppose we are given a hidden random variable K hat that takes value K with probability CK modulus squared. And the probability of getting M hat is the output we get from quantum phase estimation. So this distribution, we can write it down in this way. So we think of it as some variable that depends on K hat. So there's a conditional probability distribution going from K hat to M hat, and then this multiplied by the probability distribution of K hat gives us the distribution of this M hat. So the conditional distribution is completely specified by the kernel. And this is completely specified by the CK, which comes from your initial guess. So K here has a physical meaning. It's indexed for the eigenstate. And the conditional probability is the probability of getting energy measurement M hat given an exact eigenstate psi K. But we don't have exact eigenstate, so here is the, yeah. So we need to show that this probability is concentrated around this thing, which corresponds to the eigenvalue. So if gamma were indeed a Dirac delta function, then this probability distribution will be completely concentrated at this single point, but it is not. So we need to characterize this concentration. So we denote this delta theta by the to be this energy measurement error. So tau lambda k is the rescaled energy, and this is the actual thing we measure from quantum phase estimation. And you can write it down this way, for which we have the closed form expression. So we can plot out this function. It looks like this. So you see delta theta is very much concentrated around 0. So basically, it resembles the Dirac delta function, but we need a rigorous statement of what this means. And here I'm only looking at the interval between minus pi and pi. Actually, this kernel is 2 pi periodic, so you can only determine everything up to a 2 pi phase. And so we define the energy measurement to be this thing. So this is what we read out from the phase estimation circuit. And we define a distance on torus in the following way. So because there is this 2 pi ambiguity, so we define distance on torus x a to be this. So and the concentration of this kernel guarantees that if we look at this modulus distance between the thing we actually measure and the exact eigenvalue, we will have that the probability of error being larger than epsilon is upper bounded by 1 over 2 to the r times epsilon. So 2 to the r is essentially how long you need to run the time evolution. And this is true for every k hat equal to k. So this gives us an operational understanding of what quantum phase estimation does. So we first example this k hat with probability ck squared. And ck is completely determined by the initial guess phi. So ck are basically just the coefficients coming from it. And we do not actually do this, and we have no access to k. This is something we do in an imaginary way. So that's why I call this k hat a hidden random variable. And energy estimated tau times lambda hat is generated from running QPE, and it is epsilon close to the actual eigenvalue, with probably at least this much. So we can just increase r to make this thing arbitrarily close to 1. So in this sense, we're sampling from the spectrum of H. And each sample is close to a rescaled eigenvalue with large probability. So it becomes exact when we take the limit of r going to infinity. And so this expression tells you how large r needs to be. So the rescaled eigenvalues are determined modulo 2 pi, and therefore we need to choose tau appropriately to get lambda k to resolve this ambiguity. So basically everything depends on this concentration inequality, right? So we want to make sure that error being larger than epsilon is small. So yeah, I've written down a proof of the inequality here, but actually how much time do I have left? Yeah. Okay. Yeah, so are you guys interested? Maybe I can just skip through it. Okay. Yeah, so let me skip the proof. But the takeaway is there is some kind of concentration going on in the kernel. Like, yeah, so to summarize, or the quantum phase estimation returns an energy estimate that is close to a random eigenvalue of h. You have no control over which one it is, and with large probability. So it can go totally wrong if your r is too small, but you can increase r to make it close to an actual eigenvalue. So for a precise statement, so quantum phase estimation returns a random variable lambda hat that's epsilon close to a random eigenvalue with probability that is very close to 1, this close to 1. And this which eigenvalue it is depends on the ck. So the runtime of the algorithm can be analyzed in the following way. So we need to apply controlled e to the minus I tau h 2 to the r many times. So the cost is basically linear in 2 to the r. And 2 to the r needs to be of order epsilon inverse in order for this probability to be close to 1. Right? So that's basically the cost. You need epsilon inverse total runtime. And so far, we're just sampling from the spectrum. We're getting some eigenvalue. We don't know what that is. But we are mostly interested in the smallest eigenvalue, right? So what if we use that for ground state energy? So recall the ground state energy is lambda 0, the lowest eigenvalue. So we need to ensure that energy we get corresponds to the ground state rather than some excited states. So what we do is that we generate many examples for lambda hat and take the minimum. And how many do you need? You need 1 over C0 squared many in order to ensure that at least one of the examples correspond to the ground state. And but in the process, we need to make sure that in all of these examples, the energy estimate is close to some eigenvalue. Like we need to make sure that none of them is like wildly wrong. So in each of the examples, this is the probability of getting the correct estimate, and you need to make sure it's true for this many times. So that gives us so we need to make sure this whole thing is lower bound by some constant. That means we need to make sure that epsilon times 2 to the r is lower bounded by 1 over the modulus C0 squared. So this tells us how large 2 to the r needs to be. So instead of just 1 over epsilon, it's now it's now 1 over epsilon times 1 over C0 squared. So the total cost for getting the ground state is now like this. So we need to run the whole thing for 1 over C0 squared many times. Each time we run, we need this much cost. So this is basically 2 to the r we have from before. So this is the total complexity you end up with. So you see the cost depends on C0. We don't actually need to know what C0 is. A lower bound is actually sufficient. So we just assume that C0 squared is lower bounded by some eta, and the total cost will scale like epsilon inverse times eta to the minus 2. So this achieves the Heisenberg scaling instead of in terms of this epsilon, because you get this 1 over epsilon scaling. And here you no longer need the exact ground state. So 2 to the r is how deep the circuit is in each run. And it scales like epsilon inverse times eta inverse. So this is the circuit depth. And r is the number of Anzilla qubits. So we basically just take the log of the circuit depth, and you get the number of Anzilla qubits needed. So Now to summarize, we have looked at two algorithms for finding the ground state energy. So what I've described, like just then, is the textbook version of quantum phase estimation. So there are many, many other versions. Some give you better scaling, but they are also they also require some more complicated procedure. So the simplest version is called textbook version, which I've already introduced. It can give you the ground state energy with an imperfect initial guess, but requires many ancillary qubits. This previous example we have seen, which is based on a Harvard test, can give you ground state energy using a single ancillary qubit, but it requires a perfect initial guess, right? Both achieve the Heisenberg limited scaling. So now the question is, can we have all the good features? Can we have a method that uses an imperfect initial guess, uses a single ancillary qubit, and also achieves the Heisenberg limited scaling? So that I will cover in the next lecture. So that is what we call the early fault-tolerant quantum algorithm. So yeah, with that, I want to thank you for your attention. Any questions?